Hi, welcome to this experiment on finding the refractive index and predicting the critical angle. So for this experiment, we have a semicircular glass block and we pass an incident ray and try to find out the angle of incident and angle of refraction. And the reason we use a semicircular block is because any ray that passes through the semicircular block is always passing through the normal because the normal is the line from the radius to the circumference, right? Any of these is a normal to this curved surface. So any ray that's pointing, that's coming in will always pass through the center. So we don't, the angle of incident for this case is 0, so the ray will come straight in. So that's why we use this semicircular block. And once you know the angle of incident and refraction, we can find the refractive index. So here is the setup. So in this setup, we have this light ray box, and here is a cylindrical disc or semicircular disc, the glass block, and then here is a protractor which we use to measure, right? So you can see that the incoming ray is passing straight in. And now I'm going to slowly tilt this, so give it a little bit larger angle of incidence. So there you go. Oh, sorry, I will do the other way. Okay, there you go. So you can see that as I am doing this, there are two rays that's coming out. One is the ray that goes like this, and that is reflected, and this one is a refracted. So there's both refraction and reflection that's happening. So let's increase it and let's set it to about 60 degrees. So this is 60 degrees. So this is 60 degrees. You can see that from the normal. From the normal you have, from this 90 degrees, that's about 90 minus 30 is 60. Now let's mark these 2 points. The ray, you can see that the incoming ray is somewhere here, and the outgoing ray is here and here. So these points are marked. So I already knew these points, so these are already marked, and I've drawn a line. And now let's measure these angles of what is the angle. So you see that that's about 35 degrees is the angle of incidence. So that's about 35 degrees. And angle of reflection should exactly be the same. So let's see that. Yes, the angle of reflection is also the same. So this is also 35 degrees. The angle of refraction was 60 degrees. So that's this angle. So that's your 60 degrees, and the ray went out like that. All right, so let me put this back and show you again the whole setup. Okay, so initially it was like this, and slowly I changed this angle and the other way. There you go. There you go. Okay. So now let's calculate the values of, or let's do the math and try to predict the refractive index. So as you can see, I was for us 35 degrees, and this was 60 degrees. So that's sine 60 divided by sine 35, and that would be I can use my calculator. Sine 60 divided by sine 35 equal to 1.51, and that's the refractive index. Now once you find that, now what we're going to do is we're going to increase this incident angle and get to a point where this ray, we are going to reach the critical angle. We are going to hit an angle. As we increase this incident angle little by little, you will see that this ray is going to get more and more away from the normal. So it's going to go over here. And there will come a point when the ray will just graze over the surface. And that angle is the incident angle. And refracted angle is 90 degrees. So here you go. Here's the equation, which is the refractive index of the glass into sine of IC. Into sine of IC would be refractive index of air into sine of 90, which is exit angle. And your sine IC will be 1 divided by, this is both quantities 1, and 1 divided by refractive index of glass, which is 1.51. So we can punch this, we can try to calculate what that is. 1 divided by 1.51 is equal to 0.66. We can find the sine inverse of that is 41.47. So let's take it as 41.5 degrees. So that's the critical angle for us. That's what approximately we need to get. And let's see what happens, right? So first let me get back to the mean position. There you go. So incoming ray, and it goes straight. Don't mind this blue line, that's a mistake. All right, so now let's slowly change the angle and see what happens. As I'm increasing, you can see that there is a reflected angle and refracted angle, and you see, oh, that ray is, as I increase this angle, you can see this is going more and more towards the normal. It's going towards the normal, it's going towards the normal. Yeah, it's just grazing the surface at this point, and now you don't see anything out. All you see is, you see the internal reflection. As I increase this angle, you see that all the light is being reflected internally. So let me again hit the critical angle. Yes, I have kind of hit the critical angle now. Yeah, just a little bit above the critical angle, you can see that. So let me decrease, yes. So this is where I think it just grazes over the surface, and I have marked these points and these points which are already there, and this I can draw a line, or I have already drawn a line at which this happens. Let's measure that. What is the angle of that line? There you go. So you see that this is 90, this is 40, and this is 41 degrees. You see exactly that's about 41 degrees. So that's what we have. We have we have this IC is indeed experimentally we have seen that that's 41 degrees, and above 41 degrees you see total internal reflection. So I hope you enjoy this video, and you had a good sense of the Snell's law, and the ideas of critical angle. See you in the next one. Bye.